Okay, so welcome back. This is our introduction to performing monthly QA on a linear accelerator. This is going to be the second part of the introduction video. So far we've discussed the tests that need to be performed according to TG142 on a monthly basis for a linear accelerator, and we've discussed output tests, so those tests that require an ion chamber, slabs of plastic, and the beam to be turned on, and we've discussed the mechanical tests. So there are a number of other tests that also need to be performed. They can essentially be broken down into two additional categories: imaging tests and then like miscellaneous or other tests. So we're going to talk about those, and I'm actually going to go through them in the order that they're presented in TG142, so not necessarily the most logical order. So the next one in our list is going to be safety tests. So there are actually more tests that need to be done on a daily basis than there are on a monthly basis. On the daily basis, you have to check to make sure things like your audio-visual system is working, so you can communicate with patient and a patient communicates with you. Door safety tests and things like that. But on a monthly basis, the only thing that we check that is required that we check is the laser interlock system. So on a linear accelerator, there is an invisible infrared transmitter that it's actually, I believe it's a beam that is projected out of the machine, out of the gantry, and it's projected just underneath the head of the gantry. So there's the head of the machine, the collimator, the mylar sheet, which is the output window with the crosshairs, the reticle on it. Just underneath that, between the head of the machine and the patient, is a laser linear array beam, and the purpose of that is to stop the machine if the machine believes there's going to be a collision between the head of the machine and anything in the way, such as a patient or a table. It most likely is going to be the patient that is causing the interlock, or it could be a bed sheet that's been positioned around the patient. If the patient is on the table and covered in a sheet, and that sheet hangs off the edge of the table, then when the gantry goes underneath, the laser can actually see that there's something obstructing the path of the gantry, even though it's just a bed sheet, which wouldn't cause any problems. It could it would trigger this interlock, so that would be called the laser guard interlock. So we have to test to make sure that that laser is working. And you could do that just by checking to make sure that when something is in the path of the laser beam. Oh, 1 second. Okay, so after a quick distraction there, we just finished talking about the laser guard, so we will move on to respiratory gating tests. So our machine is outfitted with the ability to do respiratory gating. Both of our machines have this capability. It utilizes a camera, two cameras actually mounted at the above the patient's feet at the foot of the table, mounted to the ceiling, and it looks down. And the idea is that you place a reflective box on the patient's chest, and then as the patient breathes, the cameras monitor the position of this box. So as the patient takes a deep breath in, the box rises, and as they breathe out, it falls. And that allows you to correlate beam on with respiratory motion. So the box is a surrogate. It is not actually an indication of actual breathing. The patient could actually just be arching their back up and down, but it would still recreate. If we did amplitude-based gating, it would still recreate a beam on and off position. So we have to be careful when we're using this, that we know that we're aware of what it's doing and how this is functioning. But it is a pretty handy feature, and we do use deep inspiration breath hold and end expiration breath hold quite frequently. So we have that capability on both machines. We need to test it on both machines. So what does TG142 say that we have to do? So we have to check to make sure the output of the machine is constant when gating is used. So for example, if you shoot 100 monitor units and you get a reading without gating, and then you repeat the same measurement with the beam turning on and off for gating, the reading should still be the same, meaning that the machine is accurately stopping and starting with respiratory gating and not overdosing or underdosing the patient. So the charge collected needs to be the same. So that's called beam output constancy with gating. Phase and amplitude beam control need to be tested to make sure they're functioning. There's no tolerance for this test. So you just need to have a box that moves up and down. And if it's amplitude based gating, then as the box rises above a certain threshold, the machine is triggered and turns on, and then when it drops below that threshold, it turns off. That would be amplitude-based gating based on an actual physical position of the box moving up and down. Phase-based gating is taking the respiratory motion, plotting it out as a sine wave, and then choosing certain phases of the breathing cycle for it to be on and off. So, for example, you could have the machine turn on when it goes from any minima to any next minima. Those would be phases rather than actual amplitudes. And so you can do phase-based gating. So it's not uncommon to treat patients between, let's say, 40 and 70% of their breathing, which means that they breathe out. And when patients are breathing normally, when they actually breathe in and then breathe out, and when they breathe out, they hold for a second. So it's actually your normal breathing pattern is not the same amount of time breathing in as breathing out. You tend to spend more. You have a longer time at the breathing out than you do at breathing in. So that's what hence the using the phases at the end of the breathing cycle, and because that occurs more often. Or for a longer period of time, allowing the treatment to be a little bit more efficient. So we test that, and the test for that would be pretty much the same as amplitude-based gating. You can use a motorized phantom to do this. So basically anything that causes the reflector box to move up and down. The in-room respiratory monitoring system has to be functioning. And the gating interlock system has to be functioning. Again, this is going to be functioning if you've done the first two tests that we talked about. So nothing very complicated needs to be tested for the respiratory gating. Most of the tests only require that it's functioning with no tolerance, and then the output has to be consistent within 2%, which is the same tolerance as what you would expect for a non-gated treatment. The next test we're going to talk about is to test to make sure that the enhanced dynamic wedge is working. So our Varian machine has the capability to do wedges without actually physically placing a wedge in the path of the beam, and it does this by sweeping a jaw across the beam. So that's referred to as enhanced dynamic wedging, and we can test to make sure that this is working. So the idea is similar to that with the gating test. You test the output with and without the wedge, and you should get the same reading. So if you well, actually that's not entirely true. It should be consistent from in this case it should be consistent from day to day. So if you do an output check with a certain angle of wedge in the beam, then that reading should be consistent. So I'm actually just bringing the test up right now. So we will do this as a function of energy. So we test the wedge with 6, 10, and 18 MV on the TrueBeam. And we do the test at 10 centimeters in plastic. Let me just check. Yeah, so we're just verifying. We are actually comparing with and without and getting a ratio. and then comparing that ratio to what we expected. So shoot 100 monitor units to 10 centimeters of plastic without the wedge. With the wedge, get a ratio, which is your wedge transmission, and then compare that ratio from month to month. So that would be the EDW output check. And just like the output checks and the gating beam constancy check, the tolerance in TG142 on a monthly basis is 2%. So that's the wedge. Next up is MLCs. So we utilize MLCs in pretty much every photon treatment that we do. There is a requirement that we set 2 different MLC shaped patterns and verify that the MLCs go to where they're programmed to go. So an example of this would be setting all of the MLCs on one bank open to 10 centimeters and all of the MLCs on the other bank open to 10 centimeters. And then if you looked at that image on a graph paper with the light field, you would expect to see all the MLCs in a perfectly straight line because they've been sent to the same distance and all of them going to the correct distance. So both of those things are important. The MLCs should all be going to exactly the correct spot. And if you do that with graph paper, that would be an acceptable test to verify that they're going to the correct position. Now, they want you to do that with two different patterns. So we have 2 different similar patterns that we test for that. Another test that they want you to do is leaf travel speed. This one is a little bit trickier. What we do for this test is we actually go above and beyond here. So we actually do the tests that were provided in a paper by Ling et al. And those MLC tests are a combination of gantry motion and MLC motion. They test that the gantry speed, the MLC's speed, and also the dose rate varies correctly. Because with VMAT, all of those things can change, and they need to be all changing accurately for the delivery to be correct. So gantry motion, dose rate changes, and MLC motion all have to be synchronous. So even though TGU142 only says that we check the leaf speed, we actually check all of those things, and those are what we would call the VMAT or rapid arc QA tests. And so those tests, we perform those tests by running through some pre-programmed plans that incorporate gantry motion, dose rate changes, and MLC motion independently. And we go through those plans and we verify that everything is working by shooting beams onto an EPID and then analyzing those images in RIT. So as I said, we do more than that. The tolerance for that test is 0.5 centimeters per second. MLC tolerance in leaf motion or leaf travel speed. And then the final test for MLCs is leaf positioning accuracy at cardinal angles. So you may or may not be familiar with a test called the picket fence test. In this test, you actually have the MLCs deliver strips of exposure, and when you add up all of those strips of exposure, you should get a uniform exposure. This test can be done visually on a day-to-day basis by actually just visualizing that the pattern is correct. But it can also be analyzed in software program. So we use RIT for this at this time, which is a software package used for QAing images. And for the monthly we actually do verify it using imaging and EPID image analysis. But this test is the picket fence test, and it needs to be done on a monthly basis at each of the 4 cardinal gantry angles, so 0, 90, 180, and 270. and the accuracy for that one is that the MLCs go to within 1 millimeter of where they're supposed to. And then we're going to move on to imaging tests now. So imaging tests, we are going to test MV imaging, KV imaging, and cone beam CT imaging. So let's start off with MV imaging. First test is not just MV imaging, but the coincidence of the imaging and the treatment isocenters. So we do this using a cube. Again, we have videos on all of these tests, but you'll see us set up this cube, set it up using the lasers, take images of the cube, MV images and KV images, and verify that the images are aligned with each other. And that allows us for the 4 different gantry angles, and that allows us to conclude that the imaging and the treatment isocenters are in coincidence. So why might they not be in coincidence? Well, if you think about it, the MV beam, if the gantry is at the vertical position, shooting a beam and down anteriorly to posteriorly on the patient, so what we would call 0 gantry angle. If the machine is in that configuration, then looking from the foot of the table, the KV source is going to be to your left and the KV panel is going to be to your right. So the only way that that KV isocenter is going to be coincident with your MV isocenter is if the KV source and the KV panel are in exactly the correct position. If the position of those two things deviates, then the intersection of that axis will not be exactly at 90 degrees and at the correct position to the isocenter of the MV imaging system. So although they do move on the same gantry, there can be flex between any of those components, the KV, the MV, even the gantry head. There could be some flex, meaning that you have some drift in the KV isocenter relative to the MV isocenter. This can be corrected for in software. So if the MV and the KV panel isocenters are not into coincidence, the KV detector panel can actually be adjusted in its position to compensate, and that can be calibrated by physics. We actually have a test phantom specifically designed to calibrate the system, but at this point we're not trying to calibrate it, we're just trying to check to make sure it's correct. The tolerance for that test is 1 millimeter, so KV and isocenter, KV and MV isocenter should be in coincidence within 1 millimeter with that cube test. The next thing we're going to test is MV scaling. What this means is that when you measure the size of something that's displayed on an image with a digital ruler, the size you get is the correct size. So for example, if you take a 10 centimeter wide disc and you take an image of it, and then you measure it with a ruler, it should say that it's 10 centimeters. And I mean like a digital ruler on the machine. It's also going to be dependent on the position of the object that you're imaging, and also the position of the panel. Right. So if the panel moves down, then the amplification factor gets bigger. Is that correct? Well, definitely changes, right? So as the panel moves up and down, your magnification factor changes, and that's what's referred to here as scaling. The scaling refers to the magnification. So the image that we're trying to the thing that we're trying to image should also always be at isocenter. So that rules out the position of that vertically, but the panel needs to be in the correct position, and the machine needs to be able to incorporate that correct position into the scaling, into the digital tape measure. So if you measured a 10 centimeter disc with the panel up close to the disc, you should still measure, even though the image is bigger, you should still measure 10 centimeters with the digital ruler. And if you move the panel down, even though the image gets smaller, you should still be able to measure 10 centimeters with the digital ruler. So how that digital ruler works, how many pixels correlates to a physical distance, is dependent on where that image is. For this test, we move that panel to 2 different positions and verify that something of a known size is actually measuring to be the same size. So that's the scaling test, and the tolerance for that is 1 centimeter, verified at 2 different EPID positions. The next test is MV spatial resolution, and I'm going to lump this one together with another test, which is MV contrast and MV uniformity and MV noise. These can all be tested simultaneously with one image of one phantom, and that phantom is called the Las Vegas phantom. So to see what the Las Vegas phantom is, jump to our other video that shows us actually performing this test, but just for right now, the Las Vegas phantom is a block of aluminum with different sized and different depths holes. The smaller the holes are, the more testing it is of your spatial resolution, and the shallower the holes, the more testing, the more difficult it is for your system to be able to distinguish between, and therefore that's contrast resolution. So we test all of those using the Las Vegas phantom, and we compare it to a baseline. And the baseline, how many disks we expect to see, is stored in our monthly QA spreadsheet. Uniformity and noise can be used by checking an area of the phantom and basically using a dark field image. So we would take acquire a dark field image, which is an image that doesn't have any exposure. So it really doesn't matter in this case that your Las Vegas phantom is there or not, because you're not actually you're not shooting the beam of radiation, you're just turning the detector panel on and then off to acquire an image with no radiation, a dark field. And uniformity and noise can be acquired from that dark field image. Okay, so that concludes MV imaging. We're going to do very similar things for KV imaging, but we're going to use a different phantom. This phantom's called the Leeds phantom. We're going to test imaging and treatment coordinates coincidence. Again, that's the cube test. We're going to check the scaling and the magnification by moving the KV panel up and down this time. And looking at, the digital ruler on a KV image. We're going to test spatial resolution on our Leeds phantom. Instead of using dots this time, we're going to use lines, which is the more traditional way of quantifying spatial resolution, using the line pair test. We're going to test uniformity and noise using our Leeds phantom again. We're going to be able to measure again contrast, measuring disks of different densities. The bigger the difference between the surrounding material and the density of the disk, the bigger that difference is. So, for example, if the disk is lead and the surrounding material is air, that's a huge difference. That would be a very easy contrast test, and it should always pass. But if you have something that's two densities, the disk and the surrounding material being very, very similar densities, then it's going to be a lot harder for the test for the image to be able to distinguish that, and that would be where we draw the baseline as to contrast. So again, that's done using the Leeds test. Finally, we've talked about MV and KV. We've got cone beam. The cone beam imaging quality is tested using a third phantom, which is our cat fan. Cat fan is a cylindrical phantom. We take a cone beam CT of the cylindrical phantom. Inside the phantom, there's a variety of different materials and things that will show up on the image. The first test that we need to do is geometric distortion. Geometric distortion refers to the fact that if you CT a cylinder, then each of the axial cross sections should be a perfect circle. The way we quantified that is that there are a series of 4 rods that run through the cat fan, The spacing of those rods is known. Let's just say it's 5 centimeters. So we have a rod here, 5 centimeters over another rod, 5 centimeters down another rod, 5 centimeters over a fourth rod. Those 4 rods, all equally spaced with a known distance apart. You just measure those distances with a ruler, and that gives you your spatial distortion. CTs are not really prone very often to spatial distortion. It's actually more of a common issue in MRI because of the fluctuations in the magnetic field strength. But for CT, not so much of a problem. Spatial resolution on a cone beam CT is going to again use a line pair test. Contrast is going to use a series of disks of varying density compared to the surroundings. One thing that's kind of unique to CTs that's important is, and that includes cone beam CTs, is Hounsfield unit constancy. So we have inside the cat fan a series of different materials of non-density and non-Hounsfield units, and we can use tools to get those Hounsfield units for each of those different materials and compare them to baseline. And then uniformity in noise is basically accounted for in the same way as the other type of imaging test that we've done, and again uses the cat fan. One of the beauties of using a cat fan rather than a collection of different phantoms with different geometries is that you can just do one image, save that cone beam CT, and then do an analysis of it in software. So we actually do the analysis of the cat fan using the RIT software. Excuse me. I can't just seem to be able to sit down and not start yawning. I should probably do this standing up. So that would be the final test, the cat fan test. That concludes all of the imaging tests. So we talked about all of the imaging and miscellaneous tests that we need to do. So the only thing now is to get on the machine and do all of these tests, and those are going to be in separate videos. We're going to basically video every test that we do and explain what we're doing and how we actually set up the test and then how we analyze the test and things like that. So those will be in additional videos that are coming soon. Thanks.